Hello, everybody. Welcome to another ExpoLab blockchain speaker series. Today it's my pleasure to have Benedikt join us, and he's a senior PhD student at Stanford and has been doing a lot of exciting work around zero-knowledge proofs and sort of key technology for enabling blockchains. So without further ado, Benedikt, thank you so much again for joining us today, and please take it away.
Okay, yeah, thank you very much for having me. And I guess let's, I have a lot of different slides. I'm sure I won't get through all of them, but I think the idea is that you guys can also ask questions, and we can dive into different topics. So if we get stuck or something, or if we have a discussion about some part of it, that's perfectly fine. I don't, but I can also go on and try to teach you about zero knowledge proofs, or snarks. We'll see in a second what exactly, what is a zero knowledge proof, what is a snark, and also how these things are used in distributed ledgers, how these things are used in blockchains. And one of the key assets, or one of the key principles, this works now, of blockchains, there are kind of two key principles. One of them is this universal verifiability. So this is true no matter whether it's a blockchain that is completely public, something like Bitcoin, or something that is managed by consortium. And kind of all of them, you have this universal verifiability of blockchain rules. So all data that is written to the blockchain is public, and everybody can verify it. So every transaction that gets put on the blockchain, everyone can verify that this transaction is valid. And this, in addition, you can use this even to interoperate between chains. So you can use this public verifiability to have kind of, for example, atomic swaps. So say that transaction A on chain 1 only happens if also transaction B happens on chain 2. Because I can, chain 1 can kind of, or you can see on chain 1, or you can mirror on chain 1 what is happening on chain 2. And additionally, you have the property that assets are controlled by signatures and signature key. So what does it mean to own a Bitcoin? Well, really what it means is that you know the private key, you and no one else, ideally, know the private key to a UTXO, or something that basically that has the value of 1 Bitcoin on this Bitcoin ledger. So you know the private key and no one else to some address, some Bitcoin address, and this Bitcoin address has a value of 1 Bitcoin. Well, then you own a Bitcoin. So, and if you want to spend or use that Bitcoin, what you're going to do is you're going to issue a signature, a digital signature, a cryptographic signature, and transfer that asset. So, this is what it means to own a Bitcoin. Of course, you can, say that you trust your bank or your online exchange to manage this key for you, but that's kind of on a different level. But the problem is that we have this universal verifiability, but that seems to be completely at odds with privacy. Right? The whole idea is that all of the blockchain data is public. Well, this means that all of the transaction data must be public, because otherwise, how could I possibly verify that a transaction is valid? Well, it turns out, right, like this is the naive reasoning, all the blockchain data is public. In order to verify that a transaction is valid, I need to see all of the details of the transaction. Well, it turns out that this kind of naive reasoning, this is very intuitive, but it's not quite right, because it turns out using crypto magic and using things that we'll discuss today, I can have private transactions on a public verifiable blockchain. So I can keep the level of privacy that I want, even though I maintain the key principles of a blockchain. So very abstractly, what we're going to do, so how could that possibly work? Well, basically, the idea is that I will have the current state of the blockchain. So this is at a very high level. How can I have this public verifiability, but still have privacy? Well, the idea is that I have the state public on the blockchain, but it's encrypted. It's encrypted such that only I can see how much money I have. And then if I issue a transaction, I post the new state to the blockchain. So this is now saying, say I am sending 1 Bitcoin to Mo, and I used to have 4 Bitcoin, then the new state, the old state used to say, I have 4 Bitcoin, and I don't know, Mo had 6 Bitcoin. And now after this transaction, I have 3 Bitcoin and he has 7 Bitcoin. So I will post this new state, still encrypted. So only he and I maybe can see what this new state is. And I will post a transaction that issues the state. And what I will do in addition is I will add this so-called proof. So here, this is a proof. This is what we'll learn about today, a zero-knowledge proof. And the proof will show that the plaintext data, that the plaintext transaction data, which is inside this transaction, is consistent with the plaintext current state. So, and that the new state is correct. So basically, instead of telling you or showing you that, showing you directly and you being able to directly verifying that everything is that all the transactions are valid, instead I'm going to give you proof that the transaction is valid. And it turns out that this is a so-called zero-knowledge proof. And the zero-knowledge proof will reveal, or it will say that the transaction is valid, but it will not tell you why the transaction is valid. And we'll see in a second, or we'll see how that works. I can prove to you that something is true without revealing to you why it's true. That's the idea of of using these zero-knowledge proofs. So yeah, and a property of these proofs is that anyone can read the proof and verify them, and then they're satisfied and know that indeed this transaction was valid. So to do that, we need to introduce this tool of zero-knowledge proof systems, right? So how can we do that, right? What are these? What does this magic pie in the sky look like, right? It's a so-called zero-knowledge proof. And the zero knowledge, by the way, stands for the fact that I'm not revealing any additional information. And proof, well, basically says that, well, I'm proving to you that something is correct, right? I'm proving to you that the transaction is correct. So before we talk about these zero knowledge proofs, I quickly have to talk about something else, namely arithmetic circuits. Basically, we're going to build a zero knowledge proof for an arithmetic circuit. So what we have is at a very high level, okay, what is an arithmetic circuit? Well, an arithmetic circuit takes as input some numbers. Some of them are public, right? And some of them are variable. So x1 and x2 are variable. And then it does a set of multiplication. Then it has these gates. So the gate and does operation between the public inputs and the variables. So I have a plus operation here. I can have a minus operation, a multiplication operation, and the wiring of the circuit basically says which inputs feed into which of these gates. Okay, and you can think of this as basically once you unroll the circuit, right? You can say, okay, so what is the output of the circuit? Well, it's x1 times x1 plus x2 plus 1 times here, right? X2 minus 1. So in the end, this thing here, it basically, the output of the circuit is, it's a multivariate polynomial, right? It has multiple variables as input, and the output is some polynomial in all of these variables. So, if we have n inputs, it's an n-variate polynomial. And the circuit it's a directed acyclic graph, right? If you remember that from your graph computer science class, it means that kind of all the errors flow into one direction. So and we say usually, you know, we do this computation, we do this over a finite field. All this says is that we do all of these operations we do them modulo prime p. So, you know, multiplication, so a times b really means a times b mod this prime. And a plus b is, so what this means, all of the numbers in the circuit, you know, and all of the numbers that come out are between 0 and p minus 1, right? We'll never, you know, get over p minus 1. And the complexity of, you know, what is the size of the complexity of the circuit? Well, you know, you can say it's the number of gates in here, but it turns out really what we care about for most of these proof systems is actually just the number of multiplication gates. It's, you know, it's just a property of these proof systems that oftentimes we can get additions and subtractions for free. But, you know, multiplications are the expensive things. And so these arithmetic circuits, they're very powerful. You can basically, the reason why we use them is because you can express any computation as a circuit. So for example, if you know, want to, you can write, actually there's now compilers where you can write a C program and then you hit compile, and then basically it will output a circuit. The one criterion is that, you know, it can't have for loops, or at least not for loops where the input is variable. So, you know, because we need the size of the circuit to be fixed. One thing that circuits can also express is Boolean operations. So I can have so right, if I want to do and or not operations, I can actually express them as kind of these arithmetic operations. So an and, for example, you know, if your inputs are Booleans, so they're either 0 or 1, well, then an and will be just x times y, right? If x times y is only 1, if both of the inputs are 1, that's exactly the and condition. And or condition is a little bit more complicated. It's x plus y. Well, but x plus y can be, if x is 1 and y is 1, then that's 2. So we need to subtract x minus y, and not is just inverting x, so 1 minus x. So this gives you a way to transform a Boolean circuit or Boolean gates into arithmetic gates. So it turns out that with these arithmetic circuits, as I said, already mentioned, they're quite powerful. So for example, one thing that I can do and that people do quite often is they can write a circuit, you know, they can write a circuit for a hash function. They can say here, this circuit output 0, right? We always say a circuit is accepting, or it's valid if the end result is 0, okay? So we can, for example, design a circuit that takes as input a hash and a message and output 0 if and only if the SHA-256 hash, so there's a cryptographic hash function of the message, is equal to this digest. Okay, so otherwise the circuit will output some number that is not equal to 0. And basically the size of the circuit is roughly equal to, you know, this would take about 20,000 multiplication and addition, or it would take about 20,000 multiplication gates in order to implement this. You can actually use, you know, with other hash functions, this is actually, you can get this number much, you know, now there's a lot of work in actually designing hash functions that you can write much more efficiently as a circuit. So, you know, this might take only 1,000 gates or something. An additional thing I can do is, you know, I can have a circuit that implements a signature scheme, right? This is the cryptographic signature. So it says that the circuit will accept the input public key, message, and signature, if and only if the signature is actually a valid signature of the message under the public key. So it implements signature verification. So let's look a little bit more about, what these proof systems look like. So we have our arithmetic circuit C here, which takes as input some public statement X. So the green X is always public. This is known to everyone. And then a secret witness W. And it will say that, and then it outputs a number, and we say that the circuit outputs 0. When the circuit outputs 0, then the circuit accepts the input. And the goals that we have for our proof system are twofold. There's two different, there's two different kinds of goals that we might have. So one thing that we might want from the proof system is saying that is soundness. So a prover can convince a verifier that there exists a W such that Cx, W is equal to 0. So for example, it can convince a verifier that there exists a W such that the hash of W is equal to X, and that W is a small number. So, right, that W is between, has less than 60 bits. This is what this means. It's not, the problem though is sometimes it's meaningless to just prove that something exists. So for example, well, what's a good example? I can, say I didn't have this additional condition here, such that W is a small number. There always exists a W. If I don't put any condition on W, there always will exist a W such that the hash of this W is equal to X. The problem is just proving that it exists is not, this is not very meaningful. What I really need to prove is that I know the W such that the hash of W is equal to X, right? And so this is what we call a proof of knowledge, where the prover can convince the verifier that it in fact knows the W such that the circuit accepts, so that C of X, W is equal to 0. So if our circuit implements a hash function, this would say, I know a W such that the hash of W is equal to X. So what's the most trivial proof system? I guess, yeah, let's go back for a second. Maybe I'll ask this as a question, right? How can I build such a proof system, right? I want a proof system that satisfies, the soundness and the knowledge definition. So say now I have my circuit C and I have my public input X. How can I convince you? What's the simplest proof system that you can come up with such that you believe me that I know a W such that C of X, W is equal to 0? What's the most, the simplest proof system that I can come up with? So I guess it's the simplest proof system is I can just simply send you W, right? You can just check W yourself, right? So if I send you W myself, well, then you know that I know W. I just gave it to you, right? It's immediately trivial to verify that I know W, right? And the verifier can just check that C of X, W is equal to 0, and the verifier will accept if it does so. I'll stop for a second. This was a lot of information, so please let me know if something isn't clear, if I should repeat something here, right? Is it clear why just sending W to the verifier is a valid proof system that satisfies these definitions?
Can you explain the soundness again?
Right. So soundness says that, Soundness says that soundness just says that there exists a W, right? So we have our circuit. C is a circuit. And so let's see let's make it a very simple example. Maybe let's go back one more slide. So say, so for example here, what would be, so say this is our circuit here. What would be an input? What would be, say this is our, well, let me write something. So say this here is X and this is W. And say I set X1 to, or say I said X1 is equal to 1. What W makes the circuit be 0? So what X2 makes the circuit be 0?
So that would be like -2 and also 1, right?
Exactly, right. There's two solutions here. So there's two W's, right? There's -2 and 1, exactly, make this 0. So this is, this would be the W, the witness here. This would be a valid witness for the statement X equals 1. And what we want to design is a proof system for kind of these circuits. And I can have something similar with much more complex statements. So this is, a statement for a hash function. So when I design a non-interactive proof system, basically as a prover, I say, okay, I want to convince you that there exists a solution. This could be a polynomial this could be a multivariate polynomial that doesn't have any zeros, right? There could be no W that makes this true. And what soundness says is I convince you that in fact there exists a W that is a solution. And knowledge, it turns out knowledge is a stronger definition, right? Knowledge is it's a stronger requirement for the proof system, because if the prover convinces if the non-interactive proof has what we call knowledge, it's a proof of knowledge, well, then it will additionally say, it will not just say there exists a W, it will additionally say that, the prover knows one of the W's. It knows, say, -2, such that C of X comma W is equal to 0. Does that help?
Yep, that makes sense.
Okay.
I have a question. So where is this basically used in the blockchain terminal? I think I missed the first few minutes of this presentation. So is this used because at that point of time when the prover is trying to prove that he actually has access to the coins, something like that, at that point of time, and and
yeah,
he doesn't want to reveal the address?
You can use these proofs to prove that you have access to the coins. You can also just use a signature for that. But a signature is a kind of zero. It's a kind of zero knowledge proof. But the general theme that the general thing that zero knowledge proofs are able to provide, and we'll get to that more in a second, of how exactly that works, is blockchains have this universal verifiability property. So you can verify that every single transaction is valid. However, the problem is this seems to be at odds with providing any sort of privacy, right? It seems to mean that all of these transactions are private. And what we're now working towards is looking at these zero knowledge proofs, which say that I can actually encrypt the state. So I can have an encrypted transaction where only the sender and receiver know the details of the transaction. But instead of giving the details of instead of making the details of the transaction private, I issue a proof, a zero knowledge proof. And this proof proves, it shows that in fact, the transaction is valid. And everybody can now, see that the transaction is valid, but they don't know why it's valid.
So if I understand in terms of the blockchain, then basically, because there are all these replicas or miners who are basically trying to ensure that all the transactions are part of the ledger to ensure that there's a consistency happening. So for that purpose, instead of actually sending the transactions, you're going to make users send these proofs, and the ledger will be based on the proofs. Is that what you're suggesting?
Well, basically, I'm still sending transaction, but now I'm encrypting the transaction. So an encrypted transaction, and we'll talk about it a little bit more later, but it basically says that only right now in a blockchain transaction, say a Bitcoin transaction, the sender, the receiver, the amount that are sent are all public, right? Everybody can see them, right? And it's it seems to be, it's not a bug, it's partially a feature, right? Because you have this universal verifiability property where, all of these replicas can verify all of the transactions. And you need that, right? This is what we need to make these blockchains work. And what zero knowledge proofs, or this crypto magic, gives you is it basically says we can still have privacy. We can still, for example, say that only the sender and receiver should know, how much money is being transacted between them. And I do that by encrypting the transaction. But when I encrypted the transaction, how do I maintain this public verifiability? How do I maintain this property that everybody can check it? And this is what we're building, this is what we need these zero knowledge proofs for. Because then I can, instead of, you seeing, okay, for example, very thing that I always need to check is that the sender had enough money to, if the sender makes a transaction for 3 Bitcoin, I need to check that they had at least 3 Bitcoin, right? Otherwise we have a problem. The problem is if now everything is encrypted, I don't know how much the sender had. I don't know how much is being sent. But somehow I still need to maintain this property that no one can overdraw their balances, right? And with the zero knowledge proofs, I can prove to you, or the sender will prove to the world, it didn't cheat, but it will not tell the world, all of its bank details. That is what zero knowledge proofs give you. Okay.
Thank you. I think we'll come back to this at the later. I think I have some questions, but let's come back at later. Yeah.
Okay, great. Yeah, thanks for the questions. Keep them going. Okay, so we have this trivia proof system, right? So the trivia proof system is just sending the witness. But the problem is that the witness might be, it doesn't achieve the property that we just wanted, right? It doesn't achieve, say the witness are the transaction details that I encrypted. Well, just sending them, then we are back to square one. This doesn't help me at all. This is kind of how blockchains work today. They just send you the witness. And the other property is that the witness might be long. This might be quite a long and complex witness. And ideally, what I would want is that the proof is much, much shorter than the witness. So say the witness is 1 million, can be 1 million things long. I want that, the witness can be gigabytes long. I want that, and I can actually design proofs that are only a few hundred bytes long. And additionally, for example, also computing the circuit might be complex, and I would like to minimize the verifier's work, right? The verifier shouldn't have to do work that is proportional in the size of the circuit. And it turns out that we can actually achieve all of these 3 properties. So, yeah, so, what does this interactive proof system look like? Well, it consists of 3 different algorithms. So the first algorithm is this setup algorithm, denoted by an S, and it outputs so-called public parameters. And it outputs a proving key. Sorry for my handwriting, and a verifier key, or a verification key. And the prover will take as input the proving key, the instance, so the statement X, and the witness W, and it will produce a proof. So the prover outputs a proof, and it sends it to the verifier. The verifier then takes as input the verification key and also the instance. So this is why X is green, it's public. And then it takes as input the proof. But very important, the verifier does not take as input W. And the verifier runs some checks and then outputs accept or reject. So right, it's this triple of algorithm. So we have the setup, which takes as input the circuit, right? Notice also the verifier doesn't actually take as input the circuit. It only takes as input something that was derived from the circuit, namely the verification key, right? This goes into the verifier, and the prover takes as input instance witness, outputs a proof, and verifier says yes or no, it accepts or rejects. And the properties that we want from this proof system are threefold. So the first property is this so-called completeness property. Well, so all that this says is that if we have a valid instance and witness, well, then the prover can convince the verifier. So whenever we have a valid X and W, such that the circuit evaluated X comma W is equal to 0, well, then the verifier will accept, right? There's, this is it's basically the proof system should work. This is the, it should work for valid things. And then this other property is this proof of knowledge property, which says that whenever the verifier accepts, the prover should know, it knows a W such that the circuit of X comma W is equal to 0. So, it shouldn't be possible that the prover can convince the verifier if it doesn't know a W, which is equal to such that the circuit is equal to 0. And then we have this additional property, the zero knowledge property. And sometimes, this is an optional property. Sometimes we have this property, sometimes we don't have it. But basically what it says is that X comma pi, so the instance in the proof, reveal no information whatsoever, or especially the proof itself reveals no information about W, right? And this really means no information whatsoever. And this is kind of a magical property, right? It says that, I can prove to you that something is true. I can prove to you that, a common example is like, I can prove to you that I know a solution to a Sudoku without convincing you, without giving you any information about what the solution to the Sudoku is. And you'll be convinced that I know the solution about the Sudoku, but you have no idea what the solution is itself, right? You just know that there exists a solution, but that's basically all you learn. Okay, I'll skip over the kind of the formal definition. And then the additional property is that, so we say, I sometimes use the term proof, sometimes argument. These things really mean the same thing. Like, I hope you don't get confused by that. But sometimes we have this additional proof property, right? So we have this proof of knowledge property, the completeness property, the proof of knowledge property, the zero knowledge property. And now there's this additional property called the succinctness property. And once we have a succinct proof, we call that a snark. So I'll say in a second what snark, or a snark means a succinct, non-interactive argument of knowledge. And what this says is that the size, so when the prover creates a proof for some circuit, it says that the size of the proof is only logarithmic, it's only logarithmic in the size of the circuit. And additionally, the verifier also only runs in size, it obviously runs in time linear in X, it needs to read all of X, but it's only logarithmic in the size of the circuit. So what does this mean? Well, it means that I can prove to you that some complex computation that took 1 million steps I can prove to you that I did that computation correctly, and checking the proof, checking the snark, and then I'll produce a snark, and checking the snark, instead of doing 1,000,000 steps, 1,000,000 cycles, you only have to do 20 cycles. Or I can do a computation that is 1,000,000,000 steps, and you only have to check 30. You only have to do 30 steps or 30 different checks in order to verify this proof. So this is also completely amazing, right? This is it's not at all intuitive that this should exist, but it is actually possible, right? I can give you proof that I could outsource, I could have Amazon, on Amazon EC2, I could run a computation that takes a year, and I can verify it within I can verify that Amazon did their job correctly and the output of the computation is correctly, and it would take me let's say 20 milliseconds. So how could this possibly work? How can the verifier run in time that is logarithmic in the size of the circuit? You might ask, well, if it doesn't, if it's logarithmic in the size of the circuit, it doesn't even, it can't even read the circuit, or it doesn't even know what the circuit is. Well, as I said, the verifier relies on the fact it doesn't actually get the circuit as an input. It gets the SV, this verification key, as an input. So it relies on the fact that the setup will basically, produce a very short summary of the circuit inside this verification key. And if this proof, if the snark is zero knowledge, then we'll call it a ZK snark. So one example is that the prover can say that it knows n different inputs such that the hash of all of these values, so say the hash of a gigabyte of data is equal to y, and then the size of the proof will be, could be and we actually know how to do this, the size of the proof is like less than a kilobyte, and the time to verify it is still milliseconds. So yeah, I guess it turns out there's kind of two different types of setups. Actually, let's skip over this. So what is really interesting is that there's been a lot of recent work, in recent years, actually kind of very parallel with the rise of blockchains. There's been a lot of work in the kind of the space of zero knowledge proofs. So these things are actually, quite old. We knew like in 92 or 94, we had our first snarks, but the problem is that these were theoretically possible, but unfortunately very, very impractical. And now in, like last year and these years, there's kind of these proof systems that are getting better and better and improving on all of these properties all the time. So, there's kind of an overview of different proof systems. So, we have these Gross 16 is a very famous snark that, where the size of the proof, I think, is, I think this is like 188 bytes. The size of the proof is 188 bytes, no matter how long and it takes like 10 milliseconds to verify, no matter how complex the statement is. And, then we also have more modern snarks that they actually get a little bit, they have a little bit larger proofs, but they don't suffer from this thing called a trusted setup. Basically, a trusted setup says that the setup algorithm, if we have a trusted setup, it means that the setup algorithm is run by a person that we need to trust, right? If they cheat, then the proof system loses its soundness property. And ideally, we would have proof systems that don't have trusted setup. And so now we also have very good candidates for this. So let's pause here for a second. Is it clear, is it clear what a snark does? Right? Or what is zero knowledge? What kind of the properties of these zero knowledge snarks are? And yeah, are there any questions regarding them?
Can you repeat how a snark is different from a zero knowledge in the sense, like what is succinctness here happening? I mean, I want to know in like what part of the proof is it getting? Like, for example, in terms of blockchain, basically, I would like to know like how would a sender specify that this part is what part is it trying to prove, which will show that it's succinct or short? That's what I'm trying to understand.
So basically, these are two different properties, and ideally we'll have a ZK snark which has both properties. But the zero knowledge property is basically the property that gives us privacy. It says that no information about the witness is revealed, right? So for example, what is the witness in our example? No information about the transaction details is revealed, right? All of that stays private. So this is the zero knowledge property. The succinctness property says that verifying and checking the proof is much, much faster than actually checking the thing that I'm claiming. So what I can do is instead of, so when you download a blockchain, or you start up a blockchain client, so say a Bitcoin client, but this is true for all of them, Ethereum, whatever, when you start them, you need to go through the entire history. Like if you run a full client, if you start a miner, you need to go through the entire history and verify every single historical transaction that has ever happened, okay? So this takes days, and like starting up a Bitcoin node takes like days or weeks, to just resync it up. Instead, someone could give you a proof, they could give you a snark that the entire blockchain is valid. So then what would happen is you just download the newest state of the blockchain, you just download, the head of the blockchain. And additionally, you download the snark, which is like 200 bytes. And you verify the snark, which takes 10 milliseconds. And then you're convinced that all of the transactions in this blockchain are valid. You didn't even need to check them, right? Basically, you've outsourced that work to a prover, and now checking it is much, much faster than redoing the work yourself. This is what the succinctness property gives you, especially in the blockchain application. It lets you outsource work and lets you say, like, additionally, I could do something similar. Instead of, like all of the transactions in a block, instead of you seeing all of them and checking all of them individually, instead I could give you a snark that says, here, all of the transactions in this block are valid and they've been, applied to the state, and here's the new state. So this is, we often call this application, this is like a roll-up application, where, all of the transactions get rolled up to a prover, and that prover gives you proof that, or the miner gives you proof that all of the transactions are valid.
Okay, so before I ask this, do you have other slides to cover? Because I don't know how much longer our discussion can go.
No, let's have this discussion. I think this is probably more useful than me talking and people are being lost.
So I'll try to debate a little, and I'll try to move towards the traditional BFT protocols. So like one direction is obviously Ethereum and Bitcoin, and they talk about this using the proof of work protocol, and that is how they work. And there's other style of protocols like PBFT, Paxos style protocols, which also say there's a possibility of doing consensus using those protocols.
So this is
what I'm trying to say is that
okay, but I just want to say this has nothing to do with consensus.
Let me reach. I agree, it's nothing. What I'm trying to say is that there's some notion of called as checkpointing. You can always checkpoint the state, or in Ethereum terms, you can call finality. You can say at some point of time, I have checkpointed a state and said that all the transactions beyond this have already been finalized, and now whatever happens is that. And let's assume we have a set of replicas, a set of miners who is, there's a number which we can count. And let's assume we know the identities of the replicas and all. And we can always get these checkpoints signed by all these replicas or create a threshold signature, which is a threshold signature. So I'm just trying to understand, in such scenarios, is having a snark much more useful? Or because if I already have a checkpointed state and which is signed by using a threshold signature, do I even need snark in that scenario? That's what I'm just trying to understand.
No, so if you trust someone, right? If you trust someone that gives you the new state, then absolutely you don't need you don't need to verify all of the old transactions. But I mean, I think a lot of the idea about blockchains is removing trust, right? And even in even if you're running your consensus algorithm right now, right? Like right now, what is happening is that a miner or a consensus node that proposes a block, they propose a block with a bunch of transactions in them, or smart contracts in them, right? And they get some reward, right? Really usually incentivize the person proposing the block with, say, transaction fees or newly issued coins or something like that. The problem is that all of the other consensus nodes need to also verify everything. They need to do basically exactly the same work, other than in proof of work, but basically, let's think of like PBFT consensus or something like that. They need to do exactly the same work of verifying all of the transactions as the original node proposing this. So, here already snarks can be a huge benefit. What if we require the block proposer to say, don't let us do the work, give us a proof, give us a short proof, give us a snark that all of the transactions are valid,
So that is
right,
interesting.
we really put, like, in consensus or in blockchains, we've kind of like bundled like transaction verification and consensus nodes like together, but that's really unfair, right? And it actually leads to problems, right? Because it kind of, there's equilibria, and it really incentivizes to not actually do nodes to not actually do the work of verification. This is called like the verifier's dilemma. And snarks, like, they remedy this completely.
So that is a very interesting point. And my main concern with that point here is that the assumption here is, okay, let's assume we start with a scenario where the database is just clean, or everyone just has zero transaction. They just have some initial data. Then there are this user A and user are Alice and Bob. And Alice and Bob want a transaction to happen. They use the zero knowledge proof scenario. And basically the idea is the transaction is deduct $3 from Alice's account and maybe put the $3 to Bob's account. That is a transaction. And if you're using that transaction and we basically want this, and there are miners in traditional system, every miner would have updated this transaction in their database. They would have updated in the ledger. Now they get this proof, so they don't know anything how much is the amount in Alice's account. They don't know anything about how much amount is in Bob's account. They don't know how much amount is getting changed. They only have a proof that something valid is happening. So they all are not updating the ledger. Now the next transaction comes, third transaction, then similarly, there can be millions of such transactions. So how is the credibility of every transaction getting verified? What data is being updated in the ledger? If just the proofs are getting transferred, then what are they verifying? That's what my concern is.
That's a very good point. So this is also, this speaks to something. So there's two scenarios. One is that I can send you, this is basically, I don't know if you've learned about Merkle trees.
Yeah.
So, I could send you, for example, a Merkle tree commitment of the state. Basically, I give you, I need to and I need to do that, right? I have a commitment to the database, a small Merkle tree commitment to the database. And then I just give you a Merkle tree commitment of the new state of the database. And I give you proof that the state transition between the old state and the new state was valid, right? That it only included. But additionally, you're absolutely right that there is an issue here where, this is sometimes called the data availability issue, where nodes, what if no one knows the state of the database anymore, right? Like, and usually what we do in these systems is that actually you are required to still, like for this to work, you're required to still publish the kind of the delta. So you still have to say, okay, Alice, now Bob has balance, or Alice sent to Bob three Bitcoin. But you only basically, we can really, minimize the amount of data that we have to send. So for example, if there's some complex, smart contract or some complex transaction verification logic that has to be run, all of that can be compressed into the snark. And, no one needs to, the miners just kind of, they need to update the database, and like you kind of just send them the minimal diff such that they can correctly update the database. But all of the kind of transaction verification logic, that gets all outsourced to the snark or by the snark.
Okay, so yeah, that part I agree. And then going back to the Merkle tree part, even the Merkle trees are created by the node itself. And for that, nodes have an identity of the transaction, or at least they know what the database is, because then only they can create the Merkle root. Otherwise, they cannot do that.
Absolutely right.
And as you said,
it's important that more people, that everybody, like that at least some nodes or some honest miners, have access to the data in the database. That's absolutely true. Yeah. Yes,
and basically, then in that case, we would need some form of the database to be known, maybe some form of the state to be known. So again, it's an interesting question, like how much privacy are we providing? I mean, we can see, but ultimately, if the database, even if I don't know what the transaction is, but if I know the read and write sets of the transaction, I know how much data is being transferred, like how much is the final value. I don't know exactly the value, but I know that this address has this amount, this address has this amount, final updates.
Oh, so this is, I'll get to this. So this was just, what I was talking about was just about, kind of the succinctness part. It turns out we can still get full privacy. We need, basically the way that I do it is that all of the rows of the database are going to be encrypted. They're going to be crypto, So that's, that's how I get privacy. I encrypt all of the rows of the database, and then I prove, or the users prove, only the users know what is in their database row. Okay. Are there more questions?
I think that's good. Thank you.
Okay. I'll skip over this. Kind of this. So let's talk about applications, right? What we're just discussing, this is kind of the roll-up application. So this is, kind of rolling up these transactions, and this is actually like not just theoretical, but this is now getting deployed in Ethereum and kind of boosting the transaction throughput of Ethereum by like a factor of maybe 100 or so, I think. And you can also, but what I want to now focus on is at least in the remaining time, we have like 23 more minutes, right? So I want to focus on kind of the privacy applications of zero knowledge proofs. So the first thing that we need to talk about, though, are these are so-called cryptographic commitments. So what a cryptographic commitment is, it emulates an envelope. So what Bob can do, what in this envelope, it can write down some data. This is committing to the data, and then the verifier, send it to the verifier, and the verifier can't see what is in the envelope. But later on, Bob can open the envelope, but it can only open it to what it previously committed to. It cannot open it to something that it never, it cannot open it to some other data. So if it wrote down heads, then it can only open to heads. So, this has many applications. For example, one of them is, say, a sealed bid auction. I can commit to my bid in the sealed bid auction, and then later open it to say, you know, what exactly I want to bid to. I need 1 minute to plug in my computer, otherwise I'll go offline. Okay, so right, so in the sealed bid auction, every participant would commit to its bid, and then once all the bids are in, everybody opens their commitment. So a little bit more formally, the commitment function takes in a message and some secret randomness R and outputs a commitment string. And then the verification function takes in the message, the commitment, and the randomness, and simply accepts or rejects. So anyone can verify that the commitment was opened correctly. And the two properties that we want from commitments are that they're A, binding. So this means that I cannot commit to a message 1 and a message 2 that are different with the same commitment. I cannot open it to two different things. And that they're hiding, which means that kind of the commitment itself is statistically independent of the message. So it doesn't reveal any information whatsoever about the message. So now we can use this to build a so-called confidential transaction. So in a confidential transaction, or let's first look at a normal Bitcoin transaction, and we'll see that you know, quite a lot of is actually public here. So the sender address, the receiver address, and you know, the amounts that are being sent are all public. And you know, you may have heard that actually Bitcoin provides a lot of privacy because these addresses, they don't reveal real world identities. Well, it turns out that this is actually not really true because, for example, when I pay you, you need to give me your address. So suddenly I learn, you know, what your address is. And even if you use new addresses all the time, you can do some more sophisticated blockchain analysis to kind of link these addresses together and figure out, you know, which addresses belong to whom. And there's now actually companies doing this for you. You can hire a company that will tell you, you know, I want to figure out who this address belongs to. You know, say law enforcement can go to them and say like, hey, I want to figure out who this address belongs to. And you know, they have a pretty good rate at figuring that out. So for example, you know, so all of the amounts are public, but this is actually a big problem. You know, for example, this would mean that if you receive your salary on a blockchain, it means that your salary is public, right? And people might not want that. Or additionally, if I want to use the blockchain as, you know, for supply chain payments, this is also a gigantic problem, right? It makes it almost unusable. You know, if Ford wants to buy tires from a supplier, it doesn't want to reveal on the blockchain how much it is paying, you know, per tire. This is, you know, very crucial business information. But in the blockchain setting, or, you know, if we use these kinds of transactions, well, then everything is publicly revealed. And the right, what we won't hide is the transaction fee that is sent to the miner. This is private. But you know, what we want to hide, you know, the goal now of this confidential transaction is hiding exactly the amounts. So, you know, say in our example here, we have like, if Google sends a salary to Alice and Alice gets 1 Bitcoin as her salary, then, you know, we can see exactly, you know, that Google has put in 30 to the transaction. That's the input to the transaction. And then the outputs are 1 and 29, right? And the condition that we always have for these Bitcoin transactions, a Bitcoin transaction always has some input and some outputs, right? This is, you know, this output 29, this is what we call the change output, because, you know, it's very similar to when I pay with a $20 bill, then, but I only want to buy something for $7, well, then I get $13 back in change. And Bitcoin works very similarly here, you know, that Google has a 30 Bitcoin bill and pays 1 of it to Alice, and then it receives 29 back to its own account. So we want to hide these amounts. And the first idea is that we just simply replace them with these cryptographic commitments. So, instead we have com1, com2, and com3. So commit1 is committed to with 30 and some randomness. Com2 is the commit to 1 with some randomness, and so on and so forth. So this is a little bit larger. These commitments are 32 bytes versus, representing a number I can do in maybe 8 bytes, but not that much. So not that much larger. The problem is now that if these amounts are all hidden in these cryptographic commitments, they might look like this. Well, then I cannot, I don't know how much is transferred. And especially I also don't know, I cannot check this condition that the sum of the inputs is equal to the sum of the outputs. And this condition is important for checking that no new money was created, right? If I have a Bitcoin transaction where 2 Bitcoins come in and 20 come out, well, that would be extremely problematic, because it would mean that somehow 18 Bitcoin were created out of thin air. But if I have hidden everything under these commitments, then it's very hard to tell what is valid here. Whether this transaction is valid here. So how will miners verify this transaction? And the solution is using a zero-knowledge snark. And we use actually for this kind of thing, we would use a special purpose one that is optimized for this problem. So the first thing that Alice does, so Google created this transaction. So it would privately send R2 to Alice. So now Alice knows how much money she received. She knows that she received 1 Bitcoin from Google. She doesn't actually even need to learn R3 and R1. So she doesn't need to learn what is in Com3. It's none of her business. And then Google creates a zero-knowledge snark where the statement are the commitments, Com1, Com2, Com3, and the witness are the messages, and additionally the randomness used for the commitments. And the circuit that we create, Google creates this a proof for the following circuit, this confidential transaction circuit. Well, the first thing that Google proves is that the commitments are valid commitments. Given M1 or MI and RI, I can produce comma. And then additionally, that the sum of the inputs is equal to the sum of the outputs, plus the transaction fees, but we can ignore it. Let's assume the fees are 0. And then that's actually not quite enough. I actually also need to prove that all of the outputs are greater or equal to 0. Why is that? Well, say I had a transaction where Google put in 30 and then it output, say 40 to Alice and minus 10 to itself, or I don't know, or just did 2 outputs, one of 40 and one of minus 10. Well, the problem is that the first, I can verify I can satisfy the first condition, I can satisfy the second condition, but now I've actually created money out of thin air, because I can, say I ignore this minus 10 commitment. Well, then I have one commitment of value 30 that comes in and one of value 40 that comes out. So right out of 30, I made 40, and this is, we don't want this to happen. And in order to prevent this, we need to verify that all of the outputs that are created are greater or equal to 0. So now what does this transaction look like? Well, it has the commitments in it, and then additionally has this proof pi. And because we ideally want this proof to be short, because this now gets appended to every transaction, we're going to use a ZK snark for it. And miners will accept this transaction if the proof is valid, and they learn that the transaction is valid, but they have no idea now how much money Alice has. They have no idea how much money Google has. All of that, all of the amounts are hidden. So even though, right, the miners can still store the entire database and everything, Well, the database now consists of commitments, or I said encryptions before, but really we're going to use commitments. These are a special kind of encryption, and they reveal no information about about what is what is being transferred. So I guess now I have 10 more minutes. I could talk about Zcash. I could also, give you a very high-level overview about how these zero-knowledge proofs work.
So we kind of, Benedikt, you are flexible in terms of time. So if you need to maybe an extra 5-10 minutes, that's totally fine.
Yeah, no, I think I'm okay. I'm just wondering what is more interesting for the students.
I think so far it's been very interesting. So we'll pick
maybe the question is, would they rather see how Zcash works, or how these zero-knowledge proofs actually look like under the hood?
Might be a good idea to look at Zcash, I think.
Okay. So so if you can see, well, the problem here in these confidential transactions, I've hidden the amounts, but I've not actually hidden who is paying to whom, right? You can still see that Google is sending money to Alice, right? None of that information gets hidden. So what Zcash does is it additionally also hides who's sending money to whom. So it gives you fully private payments, kind of like cash, but across the internet. And obviously, this is a question is that this can be used for good purposes. If you're, say, a political dissident, and you live in a suppressed under a suppressing government, for example, in I think in Venezuela, people were are using Zcash and using cryptocurrencies because they're strong monetary controls. But of course, you can also use this for illegal things, right? You can use, if you have these fully private payments across the internet, you might be able to use them to buy drugs or something like that. But we're not here to judge, we're here to learn how it technically works. So kind of the Zcash blockchain actually supports two different types of payments. So it supports, very like basically it has Bitcoin running on it, like the normal version of these parent transactions. They look exactly the same as in Bitcoin. And then it has these shielded transactions. And these are completely anonymized. So the way that a shielded transaction works is that I have a shielded address, and the public key here, I have a secret key, which is a random, it's just a random number. And the public key is the hash of that random number. And the secret key is needed in order to spend the transaction, for this address, public address PK. And so if I have, then I might have a shielded node. So this is some money that I control, at this address PK. And the shielded node has a value V. So this is how much money is it? And then there's this random value R assigned to it. So I get that, whenever I get paid, I receive the info, how much money did I get paid? And I also receive this random value R. And on the blockchain, every coin on the blockchain is the hash of the public key and the value. So this is, address PK has value V, and additionally with this value R. So this is a commitment to PK and V. So on the blockchain, we put this commitment to PK and V. And yeah. So the blockchain will contain this list of coins okay? And so these are all hidden coins, none of them reveal any information. I now have committed to not just the value, like in a confidential transaction, I've also committed to who's the owner of this coin. And this is all publicly stored on the blockchain, or actually, just the Merkle root is kind of stored on the blockchain. And additionally, there's this list of nullifiers. So the list of nullifiers says that it's one entry per spent coin. And why do I need to keep this list of nullifiers? So every time I spend a coin, I publish a nullifier. And then basically this prevents me from spending the same coin again. So if I want to spend the same coin again, I would have to publish the same nullifier, but then everybody can see, oh, this node has already been spent. So you can never, this would never be accepted. So this is how I prevent double spending. So what does the transaction look like? So the owner of a coin wants to send the funds to some other address. So it wants to send it to some shielded address, PK and V prime, and also to some public address, so V prime prime. And what it will do is it will construct a new coin, coin prime, by choosing a random value R prime, and it puts in the value PK prime and V prime and sends it to the owner of PK prime. And then it computes this so-called nullifier. So the nullifier is the hash, basically it's the hash of the secret key. So whenever I try to spend the coin, I will, I will come up with the same nullifier, right? This is always the same. It's the hash of the secret key, and it's the index of the coin in the Merkle tree. So, maybe this is the 100th coin. So even if I try to spend it twice, I will come up with the same nullifier. So this is used to cancel the coin, right? Because I don't want to reveal which coin am I spending, but instead I will produce this nullifier such that if I try to spend it again, it will result in the same nullifier. And the miners will learn, and then we'll see in a second that I'll do a zero knowledge proof, but the miners will learn that some coin was spent, but they will not see any information about which coin is spent. So how does that work? Well, I produce a zero knowledge snark, which has as its statement the current Merkle root, the coin prime, so this is a commitment to the new coin, the nullifier, and then whatever public value I want to publicly output. So this is the non-shielded output. And as the witness, it has kind of the contents of the commitment, so the secret key, the value, and the randomness, and the contents of coin prime. And then it also has a Merkle proof that coin is part of, it's in this list of already existing coins. And now the circuit that I'll produce the zero knowledge proof for just says that, well, coin was a valid, it says that the Merkle proof for coin is valid. So I'll prove to you, I won't actually make the Merkle proof public. Instead, I'll prove to you in zero knowledge that this Merkle tree proof is valid. So that coin was in the list of already existing coins, that coin prime is validly constructed, that, I don't have any, this is the same condition as in the confidential transaction, and that the nullifier was constructed correctly. Well, and now all that the miners will see is they will see coin prime and they will see the nullifier, but they will have no information about which coin was spent. So now I've completely hidden, who the sender was and who the receiver was, right? All I see is this new magical commitment. It looks like a random string basically to a new coin, and a zero knowledge proof that says that, well, one coin was spent, but I'm not going to tell you which one. So yeah, here it's already also written down. So I sent to the miners the coin prime, this commitment, the nullifier, the transparent TXO, and the proof. and I will send to the receiver. Well, the receiver needs to know how much money it got paid, so it receives V prime. And then the miners will verify the proof pi, they will verify the parent output, and they will verify that the nullifier only appeared once. So this prevents double spending. And everything is valid, well, they will add coin prime to the Merkle tree of already existing coins, and nullifier to the nullifier, and NF to the nullifier list. So the transaction hides which coin was spent, and it hides the address of the owner and how much money coin prime has. And the miners, in the end, the miners can verify that the transaction is valid, but they learn no information about what the transaction details are. Okay, so this is the high level takeaway. If this was too much detail, then the very high level takeaway is that I can basically use zero knowledge proofs to give you full privacy, even on a completely public blockchain. And yeah, that's why you should care about them. So yeah, I'll, we're just in time for the end of the lecture, but I'm happy to stick around for a few questions.
Great, thank you so much. Excellent, in-depth overview of zero knowledge proof. So any questions besides that student wants to kind of listen to more details on the actual proofing part, but I guess we need to do that some other time.
Okay, so I'll
I mean, more than welcome.
I can. I guess I'll give you an example of how, like, the very simplest example of how can it be that I can prove to you something in zero knowledge? So so you may have heard or thought of the kind of the Pepsi Coke test, right? So this is like the test of whether someone fun party trick that's your kind of party, then you can test like whether someone can tell the difference between Pepsi and Coke, or Coke and I don't know, or Coke Zero. And what you do is, how do you do this? Well, you just have two glasses. In one of them you put Pepsi, in another one you put Coke, and then you write on the bottom maybe which one was Pepsi and which one was Coke. And then the tester, which is going to be the prover in this example, well, it tastes both of them and tells you which one was say Pepsi. And if the prover is correct, well, he may have gotten lucky, but there's some indication that he might know, that he knows the difference between Pepsi and Coke. But we can repeat this experiment over and over again, right? We can run this twice, swap the glasses, just clean them, do it again. And then the chance that he got lucky, if we do it once, the chance that he gets lucky is like 1/2. If we do it twice, the chance that he gets lucky is 1/4. But if we do this like 100 times, the chance that he gets lucky every single time is completely negligible, right? This doesn't happen. So, but it turns out, so this is clearly a proof, right? If I run this often enough, this is clearly a proof that someone knows, or the tester knows the difference between Pepsi and Coke. But by checking the proof, did you learn anything about the difference between Pepsi and Coke, right? Are you now able, if you see this person, do this over and over again, are you now able to like have the same, magical ability of testing the difference between Pepsi and Coke? No, you have not, right? Like this is actually a zero knowledge proof, right? It's a very simple and dumb zero knowledge proof, but it is a zero knowledge proof because you learn no information. Like the witness here is, what is the difference, the magical formula between, what is the difference between Pepsi and Coke? But if you verify this, right, if you run this test, you learn no information. You have no information about what the, unless you know it yourself, right? But from this experiment, you learn nothing about what the difference between Pepsi and Coke is. So this is actually, a zero knowledge proof for showing that, I know the difference between PEP Cinco. It's a very, kind of simple example, but it shows you that I can prove to you that something is true, or, that I know something without giving you any additional information. I can also actually use exactly the same protocol. Like there's this cute paper on saying, I can use the same protocol for showing, say I want to prove to you that I'm not the murderer of a crime scene. So if, say there was a crime scene and we have DNA, but I want to prove to the FBI that I didn't commit the murder. But I'm very privacy, I'm very concerned about my privacy, and I don't want to give my precious DNA to the FBI. So what we can do is that, I put I give a sealed envelope, that they can't open, of my DNA to them. I seal it such that they are not allowed to open it. And then they take the murderer's DNA and my DNA, and they shuffle it, behind their back. And then they give me the two different DNA samples. And if I'm able to tell the difference between them, well, then my DNA must be different from the murderer's DNA, right? But if they're the same, if I was the one who committed the crime, well, then I will not be able to tell which one was, the one that I handed them originally and which one was the crime scene one. So, this is, but if they're different, I can, answer this every time. I can say, oh, here, this is my DNA. Like, this is the one that I gave you. But if I committed the crime, then I cannot do this. So this is a zero knowledge proof of not murdering. And it turns out that, like, the funny thing is, these are kind of these sample, these like fun game examples, but it turns out that, the real protocols are actually not, that far away from it. Does that give you some intuition?
All right. So thank you so much, Benedikt, and for taking the time and joining us today. So on behalf of ExpoLab and UC Davis, really thanking you.